they dock with the space station. So basically, at any given time, Raven can tell you where the incoming visiting vehicle is in space relative to the space station and what attitude or pointing direction it is.
Raven sends the data it collects from tracking and observing incoming spacecraft to its processor or brain, called SpaceCube. This information then tells Raven how it needs to move to continue to track the spacecraft and gauge relative distance and positioning. NASA engineers have taken what they've learned from multiple Raven observations over the years to adjust and fine-tune the relative navigation system as needed, so it's ready for the upcoming on-orbit servicing, assembly, and manufacturing 1 mission, which will robotically refuel a satellite, among other things.
Raven is a sensor system that can image an object, process those images on board in real time with advanced algorithms, and calculate the pose of the object relative to itself.
These factors come together to create something like spacecraft autopilot. Much like a self-driving car can maintain cruise control based on the speed of the vehicle it follows, 2 free-flying spacecraft will be able to dock with one another using this technology. Though this operation is similar to the autonomous docking of visiting spacecraft to station, Raven's unique application is necessary for docking 2 satellites with the challenges of each moving and rotating in every direction during the rendezvous and docking phase.
Using that information to then guide the first spacecraft to autonomously rendezvous with and dock with the second spacecraft. So that means finding it in space, aligning with it appropriately, and then bringing the 2 vehicles together without smashing them into and destroying each of them, all without human intervention.
This capability is the kind of thing you need for docking with spacecraft that were not originally designed to be docked with and serviced, which happens to be a vast majority of them. That's why Raven's time on station is critical for the future of on-orbit servicing, assembly, and manufacturing, or OSAM. The OSAM-1 mission will use Raven's relative navigation capability to autonomously, meaning no humans involved, rendezvous and dock with the satellite, and then telerobotically refuel it. This will be the first time in history a spacecraft not originally designed to be serviced will be refueled as a means to extend its operational life. Raven is also important for future exploration missions.
Raven's technologies can be applied to future NASA missions because if humans want to make a footprint in the solar system beyond low Earth orbit, which is where the International Space Station is located, we're going to have to rely on some form of autonomous docking technologies in the future. Whether it be an unmanned cargo vehicle meeting up in orbit around the moon, refueling tankers located in geosynchronous Earth orbit, or a return vehicle arriving on Mars in advance of a crewed landing, all of these feats will require the technology we're developing with Raven.
Using its 3 eyes, Raven is looking to the moon, Mars, and beyond.
Relying on highly robust autonomous systems becomes more crucial the further you move away from Earth as the communications time increases drastically. Once you move past low Earth orbit, it becomes very impossible for humans on Earth to do these highly complex maneuvers in real time. It's more efficient to allow computers to perform these sequences autonomously without human intervention.
Although Raven has successfully concluded its main mission objectives, it remains on station. Meanwhile, its team on the ground is using what they've learned to develop more never-before-seen technologies that will enable future space exploration.
Before I started digging in that other bag, here you go. Yeah, no problem.
If you need to fix something in space that wasn't designed to be fixed, it's going to take all the experience you can get. With that in mind, when the International Space Station's Alpha Magnetic Spectrometer, or AMS, needed repairs, NASA's Johnson Space Center and Goddard Space Flight Center used their joint expertise to make it happen. At Goddard, that expertise resides in NASA's Exploration and In-Space Services Division, or NEXUS, which evolved from the office that was responsible for the Hubble Space Telescope servicing missions. Key to these missions was the development of specialized tools. While you've probably heard of Hubble, you may not be as familiar with AMS, so let's start there. Designed for a 3-year mission of sifting through cosmic ray particles, AMS has been looking for signs of dark matter from its position on station since 2011. Hundreds of researchers have used the data collected to investigate the source of the mysterious substance to help us better understand the origins of the universe. To continue this important data collection, AMS needed an upgrade due to general wear and tear from the harsh environment of space, specifically a new cooling system. A repair could extend its life beyond what was originally planned. Sounds easy enough, right? In fact, due to the instrument's complexity and the fact that it was not designed to be repaired, even gaining access to the system to replace it was difficult. AMS's design did not incorporate the kinds of interfaces that make spacewalks easier, or have the ability to be serviced with traditional multi-purpose tools. And so, over the course of 4 years, NASA got to work designing and developing some of the most complex spacewalks since the Hubble servicing missions in the 90s and early 2000s to fix AMS.
The AMS tools themselves were unique. They were built specifically for this task, a task that was never intended to be performed on a spacewalk. And so that required a lot of thinking about how we were going to get inside so that we could access the tubes that we needed to cut into and then install the new thermal control system, but also how to put handling aids on it so that we had a place to attach our tethers, to attach our foot restraints, to have handholds, have a place to attach equipment that we needed out there.
NASA developed 20 specialized tools to make the job possible, and on November 15, 2019, astronauts Andrew Morgan and Luca Parmitano got to work. On this first spacewalk, astronauts needed to get access. By design, 5 of the tools could be seen floating off into space, attached to the debris shield that was removed to give the astronauts access to the heart of AMS.
The debris shield handling aid was one of the first tools that Luca installed on the EVA, and this gave us a handhold to install on the debris shield to work from, but also a handle for me to hold on to ultimately when we jettisoned it overboard to the aft side of the ISS, which was a lot of fun to do.
The astronauts continued with 3 more spacewalks over the next 2 months, using all of the specially designed tools. One such tool was the Tube Cutting Guide, which was a direct result of multiple practice sessions at Johnson Space Center facilities like the Neutral Buoyancy Lab. While practicing, astronauts communicated the need for a way to identify and verify the correct tubes to cut, since they all look the same to the astronauts' eyes